Okay, hello everyone. So this is the first lecture of this semester. It's units and measurements. Now this is the first chapter of your textbook as well. And when you go over these lectures, when you watch these lectures, it's a good idea to keep the PowerPoint slides open. Because I use PowerPoint as an outline to my lectures. You can find these PowerPoints there in your World Classroom under the Files tab. So if you go to Files, you see there's another subfolder named Lecture PowerPoints. So in that you can find all these lecture slides. So I use them as an outline to my lectures. I use the diagrams from the PowerPoints. I use examples from the PowerPoints. So therefore it's really helpful if you either print them, keep them with you, or keep them open on your computer. When you are going through these lectures, you can always go pause and go back to the PowerPoints and see what's the next example is, or what the diagram actually looks like. So having said that, so let's start with the first topic. Now under this in this chapter, so these are the subtopics we have. So we have this measurements and uncertainty. We're going to talk about significant figures. We will introduce the main units, the units that we mostly use throughout the class, and how to go back and forth between the units we use and to the other units that are out there. So some important unit conversions, and then we'll talk about another topic called dimensions and dimensional analysis. Okay, so let me erase this and then add a small diagram to this. Alright, so again I'm taking this diagram directly from the PowerPoints. I'm gonna draw it here as let's see whether I can draw this clearly. So what we have is a piece of wood. So we're trying to measure the width of this piece of wood, right? So this is a piece of wood. In physics, we always come across a lot of measurements. It could be a time measurement, it could be a length measurement, or a mass or force measurement. So how do we do these measurements, and what are the rules we're going to follow? So here I have this piece of wood, and then I'm going to use this ruler. So I have this meter stick, right? So one end says 0, over here says 0, and then it's divided into these centimeters, these little segments called centimeters. So these are in centimeters, like 1, 2, 3, 4, 5, like that. And each centimeter is divided into these little pieces, 10 of those. These are called millimeters, mm. So 1 millimeter is 1/10 of a centimeter, or 0.1 centimeter. In other words, you can say 1 centimeter has 10 millimeters inside them. 1 centimeter is about this big. This is a 1 centimeter. There's 10 of those little millimeters inside, right? So I'm going to take this meter ruler and I'm going to place it like how you normally measure the length of something or the width of something. So I'm going to place the ruler like this. Okay, so one end is directly aligned with the edge of the piece of wood, and the other end over here. Now if you go back to the PowerPoint slide and take a look at this example problem, you see 0 is here, and 8 centimeter 8 is over here, 9 is here, and it's aligning with, let me see exactly where. I'm gonna go back to the PowerPoint. So it's gonna align with the line number 8 here. Okay, so how do I express the width of this ruler? I have 8 centimeters plus 8 millimeters. I can say now this is 8 millimeters is equals to 0.8 centimeters, right? So I can say the width is 8.8 centimeters. Now, how accurate is this measurement? Is there any error in it? Am I certain about this, or is there any uncertainty in this measurement? Alright, hold on 1 second. Okay. Alright, so when I look closely, I see that the edge of the piece of wood, so here's the right hand side edge, and here's my ruler. This is the 8 centimeter and these are the little millimeters. This is the 8th millimeter, and here the 9th millimeter. So let's say, just forget about this thing, 8th millimeter and the 9th millimeter. So the edge kinda in between these two lines, right? I can't say for sure whether it's close to 8 or whether it's close to 9 or whether it's right in the middle. I can't say for sure, and I don't have to go into that much details. What I'm gonna do is I'm gonna introduce a little uncertainty into this measurement. So how do we do that? So we go back to our measuring device. Now our measuring tool is the ruler, right? And in that, the smallest measurement I can make is 0.1 centimeter. The ruler is divided into centimeters and also it's divided into millimeters. The smallest measurement I can measure using this particular ruler is 0.1 centimeter, either 1 millimeter or 0.1 centimeter. That becomes the uncertainty of the measurement. So how do I give the answer? With uncertainty, the best way to write it is the width is equals to 8.8 centimeters plus or minus 0.1 centimeters. Plus or minus, this tells me there is a room for this to be a little bigger or a little smaller. By looking at this, you can see it is between 8 and 9, so it's mostly plus 0.1 centimeters, but it is a standard that we add and subtract both, plus minus the uncertainty piece. So you can rewrite the same thing if you want to. You can do it this way as well, 8.8 plus or minus 0.1, and then put the centimeter after everything. So this is how you express the record an answer, a measurement with its uncertainty. All right. Okay. Okay, so with the uncertainty, another thing sometimes we need to calculate is the percentage uncertainty. So now percent uncertainty. So this tells you how much how much influence this uncertainty has on your answer. So for an example, in this case, our measurement of the width is 8.8 centimeters. Our uncertainty, or we say the change, or delta, this little triangle sign is called delta, or the change. It stands for change. The delta portion of the width, or the change of the width, is 0.1 centimeters. So percent uncertainty is the delta portion divided by the actual measurement multiplied by 100. So this gives you roughly 0.1 divided by 8.8 multiplied by 100 is approximately about 1%. So you can say, here's my answer, 8.8 centimeters with an uncertainty of about 1%. So if you get an uncertainty of, let's say, 50%, that means it's not a very good measurement, right? If you get an uncertainty percentage, a percent uncertainty about 1% or less than that, you can confidently say it's a good measurement because your answer is fairly close to the actual value. So we make measurements, we make uncertainty measurements, and then we calculate percent uncertainty. So all together you can get a good picture about the measurements you make. All right? Okay. So the next topic we're going to talk about is significant figures. So I'm going to go ahead and erase this. Significant figures, or sig figs. So what are significant figures? When we make measurements and then we use this measurement to make calculations, we need to know how many digits we can measure accurately or with confidence. So for an example, let's look at this number. Again, I'm taking these numbers from the PowerPoint slides. So we have a measurement. It says 23.21. So when you express this, when you write this down, 23.21 centimeters. So let's say you are making some length measurement. When you write this down, this tells you that you know all four numbers accurately, right? So that's the idea of significant figures. So another example. Let's say we have 0.062 meters. So this tells you that, alright, let me go back to this. The first one, if you write it this way, the answer 23.21, that tells you that you know this number, all four digits, reliably, right? So this answer has 4 sig figs. So these are the number of digits that you know reliably with confidence. Now this is the rule of significant figures. We do not count the zeros in the beginning, right? These are just placeholders. So if there are no actual numbers in front, we start from the first point where we see a number, which is 6. So in this case, here we have 1, here we have 2. We have 2 sig figs. In the first case, right, this is example 1, example 2. In this one we have 1, 2, 3, 4 significant figures. Over here we do not count the numbers, the zeros in the front. So if you take an example like this, for an example, 100.56 let's say kilograms. How many significant figures are there? Now there are two zeros, but there is a non-zero number in front of it, so we're gonna count all of them. So in this case we have 5 significant figures. So that's the rule of sig figs. When you write down an answer, it tells you how many digits, how many places you know reliably, right? So let's look at another example. How about this one? 800 kilometers. So in this case, since there is no decimal point here, we don't know for sure unless somebody tells you clearly how many sig figs we have. This could be 1, it could be 1 or 2 or 3. So it could be that one significant figure means you know this for you know approximately this answer is around 800. Means let's say you are measuring the distance between two cities, you have like a vague idea it's around 800 kilometers. But if somebody says okay, this has 3 significant figures, then you know for sure exactly the distance between 2 points is gonna be 800 kilometers. But if you write it this way, 800.0 kilometers, now you know for sure there's 4 sig figs. So there is a way to avoid these uncertainties, like these unsure situations. So we'll come to that in a minute. Using scientific notation we can work around these things, but before that I want to talk about another important thing comes with significant figures. So let's separate this. Now let's say you have 2 measurements. Let's say you're trying to calculate the area of a rectangle, right? So you're gonna multiply to find the area of a rectangle. What you do is you multiply the 2 sides. So let's say this side is 11.3 centimeters and this side is 6.8 centimeters. Now you're gonna take the calculator and you're gonna plug in the numbers and find the answer exactly. 11.3 multiplied by 6.8. So let's say area which is equals to 76.84 centimeter square. It's an area. We are multiplying centimeters by centimeters, so we have to put the square term telling you that centimeters has been squared, like been multiplied twice. Alright, so the answer is 76.84. Now if it is required to give the answer with significant figures, considering significant figures, how do we do that? So let's see the first part. Now we're gonna go back and see the 2 numbers we just multiplied. The first one, this one has 3 sig figs, right? 11.3, 1, 2, 3. This one has 2 sig figs. So the sig fig rule is when you are multiplying several numbers, the final answer. Now for your calculations, what I want you to do is keep all the decimal points. When you're multiplying something, when you're dividing, subtracting, whatever you are doing, you're going to use the calculator. So keep all the decimal points. only when you reach the final answer, at that point you can think about significant figures. So over here, first part has 3 sig figs, second part has 2 sig figs. So the sig fig rule is you keep the least number of sig figs, right? So in this case, least number of sig figs, you don't have to write this down when you're solving a problem, right, is 2. So the answer should have only 2 significant figures. So how do we do that? We have 76.84 which has 4 sig figs. How do we reduce this to 2? We have to round this and make sure we only have two digits in the answer. So when you do that, we have to round this to 77 centimeters squared, right? So that is the significant figure rule when you do math operations like multiplication or division. Okay, all right, so I'm gonna erase this. So the next topic, let's talk about measuring units. Now you already saw that we were measuring the width of a piece of wood, and I use centimeters. So likewise, let's talk about the most important units that we use frequently. So in physics or in research and industry, we normally use standard units or SI units. This is also called the metric system. Mostly in US, in our day-to-day life, we use the British system, where we have these units like miles, lb, feet, inches. So these are also acceptable units. But when it comes to research and technology, it's very convenient and it's widely accepted that we use SI units. And so whenever you are writing research papers or any other research related stuff, you have to stay with the metric system, right? For an example, if you're measuring some length, it has to be in meters or centimeters. It cannot be in inches or feet. Okay, so what are the basic quantities that we use all the time? We use things like length, time, and mass. So these are called the basic quantities. Most of the other quantities that we measure, like for an example the speed or the acceleration, the force, they are combinations of these base units. So these are called base units or fundamental units, and the combinations are called secondary units or derived units. So let's see what are, now these are the quantities. What are the units do we use? Units. Length, the standard unit, the SI unit is meters. Time, the standard unit is second. Actually just S. So let me take the eraser and measure this E. Okay, all right. seconds, and for mass is kilograms. Alright, so again, there's three basic units or the fundamental units: length measured in meters, time measured in seconds, mass measured in kilograms. We use different labels instead of like, let's say in a problem, when you try to solve a problem, let's say you're trying to work on a couple of different masses. You don't write down the entire word, you just use a letter symbol. So for mass, the letter symbol is M. Now don't get confused with meters here, right? This is a unit, this is a letter symbol. Time is given in T, length is indicated by little l. Sometimes we use distance, it's the same thing as length, so we use letter D. Sometimes we use letter X. So that is the thing with physics. For the same thing, you will have many different labels. Also, for many different things, many different quantities, we will be using the same letter. So it gets a little confusing in the beginning, but over the time you will get used to it. So for now, let's say the length is labeled as L. Alright, so what are the other units? Now in the metric system, we have things like kilometers, we have centimeters, millimeters, micrometers, all sort of measuring units for length. They all has this common term meters at the end. And also we have this non-metric, non-SI units like miles, feet, inches, and stuff like that. Time is measured in standard unit is seconds, but then we have hours, minutes, years maybe. And for mass we have kilograms, so then we have grams, milligrams, micrograms, and then lb maybe. Okay, so for all our calculations, most of the time we're going to stay with the standard units, meters, seconds, and kilograms, unless it's required in the problem asking you to use a different unit. All right. Okay, so the next thing I want to discuss is unit conversions, how to go back and forth between different units. So let me go back and erase this. Okay, so unit conversions. All right, so let's write down some unit conversions that we always need. Like for an example, 1 meter lengthwise. So let's talk about length first. Meter. 1 meter is equals to 100 centimeters. Think about a meter stick. You know that it's, so this is, let's say this is 1 meter. A meter stick is divided into 100 little segments like this. This each piece, so this whole thing is 1 meter, right? This is 1 meter. This little thing is 1 centimeter. And inside a meter there's 100 centimeters. Another important one is 1 centimeter has 10 millimeters in them. So if you enlarge this, like this little segment over here, right, if this is a centimeter, it is divided into 10 of these things, which are millimeters. So if I say, for an example, we have 3.56 meters. I want this to convert this to centimeters. How do we do that? 1 meter is 100 centimeters, so therefore 3.56 meters equals whatever this number, we multiply it by the meter number multiplied by 100, you get centimeters. So 3.56 is equals to 3.56 meters multiplied by 100 centimeter divided by, okay, so what am I doing here? I'm multiplying this number by 1. So when I multiply something by 1, right, for an example 12 multiplied by 1 is still 12, nothing changes. So that's the same thing I'm doing. I'm multiplying 3.56 by 100 centimeters and I am dividing it by 100 centimeters. So is the number changing? No, it's still 3.56. Instead of saying 100 centimeters, I'm going to replace that with 1 meter. Still the same, right? You multiply with 100 centimeters, you divide it with 1 meter, still this whole thing is just 1. So I'm not changing the number, it's still 3.56. Only thing happens here is the units are changing. So here you see 3.56 meters and meters get cancels out. That is this just 1 under the line, that's not going to do anything. So we have 3.56 multiplied by 100 centimeters equals 356. The remaining unit is centimeters. Alright, okay. Alright, next example. Let's say this time I want to convert 230 centimeters. I want to convert this into meters. So how do I do this? So I'm going to write 230 centimeters and then, like I did before, I'm going to multiply this number by 1. So it doesn't change it, right? But now, since I want the answer to be in centimeters, I'm going to multiply this with 1 meter. I want the answer in meters, so I'm going to multiply with meters but divide with centimeters. You see that it's the opposite, right? Opposite of what I did over here. Over here I wanted the answer in centimeters, so I multiply with centimeters, divide with meter. I do the opposite here. Multiply by 1 meter, divide by 100 centimeter. This is 1 meter and 100 centimeter, same thing, so it doesn't change this 230, it only changes the unit. So you see that centimeters and centimeters cancels out. The leftover unit is meters. So we have 230, so this is equals to 230 multiplied by 1 over 100 meters, which is equals to 2.30 meters. So this is how you do a simple unit conversion. So the book has more examples. I want you guys to take a look at them. How to go back and forth between kilometers to meters, meters to kilometers. I want to try one more example, so let me erase this. So let's try this. 25 miles. Convert this into meters. How do we do this? 25 miles. Now this is not inside the metric system, right? These are some other units. We want to bring them into the metric system. So the first thing I'm going to do is I have a relationship. I'm going to look into this. I have a relationship saying 1 mile equals 1.609 kilometers. So I have a known relationship here, miles to kilometers. So I'm going to use that first. So let's convert miles into kilometers. So we have 25 miles. I'm going to multiply this by 1. So but I want to have the answer in kilometers. So 1.609 kilometers divided by 1 mile. 1 mile is 1.609 kilometers. So this is essentially multiplying by 1, right? But see the units cancels out. So miles and mile cancels out, leaving 25 times 1.609 kilometers, which is equals to, so I'm going to use the calculator here real quick. Gives me 40.225 kilometers. Alright, now we need the answer in meters. So I need to go from, this is my step number 1, this is my step number 2. I need to go from kilometers to meters. How do I do that? I know that 1 kilometer equals to 1000 meters. So what I have to do is multiply this number by 1000. 40.225 kilometers equals 40.225 multiplied by 1000 meters. So which is this decimal point is going to move 3 times. 40.225 123 meters. All right, okay. Now if somebody says, all right, leave the answer, consider the significant figures. What do I do? The first starting point has 2 sig figs. 25 miles has only 2 sig figs. The answer should only have 2 sig figs. So I'm going to say this is equals to, this is equals to 40,000 meters and say that this has only 2 significant figures. I have to say it in words that the answer has only 2 sig figs. Otherwise we wouldn't know whether it's 1, 2, 3, 4 or 5, right? So we have to mention that the answer has 2 sig figs. Another thing I can do is, the better thing I can do is use the scientific notation. So we go back here. Our answer is 40,225. I'm going to put a comma here, meters. In scientific notations, how do I write this? 4.0225 times 10 to the power 1234. Right? This is how we write numbers in using scientific notation, right? So I have 40,225. So put the decimal point right after the first digit and then count how many digits after that. 1, 2, 3, 4, and then write it down as 10 to the power. Okay, so now if I want to leave the answer with 2 sig figs, my answer will be 4.0 10 to the 4. 2 sig figs, 1 and 2, right? If I need 3 sig figs, somebody says, okay, give me 3 sig figs. What do? 4.02 times 10 to the 4 meters. And you can continue like this. If you need 3 sig figs, you add another digit like that. All right. Okay. Alright, so let me erase this one more time. Okay, so our last topic for this section is dimensions and dimensional analysis. Let's see, what are dimensions? Dimensions and dimensional analysis. So we talk about the base units like length, time, and mass, right? So the length has dimensions of length because it's a base unit, so there is nothing more fundamental inside it. It's just the most fundamental unit by itself. The time has dimensions of time, and mass has dimensions of mass. But if you think about little complicated units, right, secondary units or derived units, for an example, speed or velocity. Velocity and speed, they have very common features. There are some important differences as well. So velocity is, how do you define velocity? It's distance divided by time, or distance over time, or we can say rate of change of distance. Now velocity is a unit, is a quantity, and when we analyze the dimensions, we see that inside velocity we have distance, which is a length, time is t, right? So dimensions of velocity, L over t. We use capital letters to indicate dimensions. Dimensions of velocity is length over time, and velocity is measured using a unit called meters per second. You see that meters is a length. It's a measure of length, right? Length is measured in meters, time is measured in seconds, so meters per second. So the unit should match the dimensions, otherwise we have done some mistake somewhere. Another example, we will come to this later on the during the course, but for the time being I'm showing you these examples. Acceleration. Acceleration is how rapidly the velocity is changing. So that is velocity divided by time. Now if you think about the dimensions, velocity has dimensions of L over t, and then we're going to divide that whole thing again by t. So this becomes L over t squared. That's the dimensions of acceleration. And if you think about the units, that will be meters per second squared. The same thing, the division can be written in a couple of different ways. Like for an example, L over t is same as L over t, like this, with this slash or backslash or whatever it is. Or you can say LT minus 1 to the power minus 1. L over t squared can be written as LT minus 2. The unit can be written as ms minus 2. This can be written as ms minus 1, right? So again, coming back to the dimensions, this is how we find the dimensions and why it's significant. When we add different quantities, the dimensions should match. You cannot add an acceleration into a velocity. If you're adding two quantities, if you're not sure about whether you can add them or not, you go back and check their dimensions. The dimensions has to be the same. It's like you have a length measurement of 10 meters and you have another measurement of something 20. We don't know the unit, but in your calculation you have to add them together. So how do you do that? You go and check whether this also in meters. If it is says meter squared or something, then you can't do this. You can add them together. The units, in order to add meters to something, the other thing also has to be in meters, like 15 meters or something, right? So that's the idea of dimensions and dimensional analysis.